Today I'll be talking briefly about what we have learned throughout this summer with Dave Fox and the HPC Academy. For my end of the internship, we were able to take a look into the installation of Flux and get a surface level understanding of how it works while facing certain obstacles with the team and creating a tutorial guide for future students. For this presentation, we'll be explaining what is Flux briefly, showing a diagram of how it works. Then we will show you our project objectives and goals, followed by a few images of some jobs we ran, and then we will talk about challenges and future goals. This is the team that was working on the project this year, and Christine will take it away for the first part.
Hi everyone, my name is Christine. I'm an upcoming fourth year at CSU East Bay studying computer science. I'm planning on graduate in May of 2023. So I'm going to be starting off with talking a little bit about what Flux is. Flux is a resource management framework. It has a job scheduling algorithm that determines when and where resources that meet specific requirements will be available. It also has an allocation policy that determines what type of job runs on what node. Flux can be compared to other resource and job management frameworks like Slurm, but Flux is designed to have a much better overall throughput, job coordination, communication, and portability due to the packages it requires you to install. On the next slide, I have a diagram kind of displaying how Flux works. So the red box can be seen as a sysadmin, and he's the one who starts a Flux instance, which then starts a Flux broker on rank 0. And this happens on a management node. And then the green frog is the user who submits jobs with commands like Flux mini batch, which then gets sent to the Flux broker. And this happens on the login node. And then on the compute node, we always have the Flux broker running because that's a background service that's required for Flux to work. And we also have Flux Shell, which is responsible for the startup and execution of user jobs. Next, I'm going to be talking about what we did for our project. So we had to install Flux on our cluster. And in order to do that, we had to install Flux Core, Flux Security, and Flux Sched. So Flux Core basically implements the communication layer, meaning how the brokers within each Flux instance talks to each other. And then Flux Security consists of the APIs for job signing. And Flux Sched uses special graphs and management schemes to schedule resources for use or determine when the resources will be available. And we also had to run MPI jobs, which I'll be talking a little bit more about on the next slide. So we started off with running the command flux mini run just to see if everything works. We passed in 4 tasks and 4 nodes, and then passed in the host name as a job, and we see that it was successful. Then we moved on to submitting a script as a job. So we tried to submit flux run hello, which is just a compiled version of the MPI program to the left. So we tested that out with Flux mini batch, passing in 4 tasks and 4 nodes again, and then finally the script. And after running that command, we can see a job ID being displayed. And when running the command Flux jobs, you can see that the job is currently in a running state. And after a couple of seconds, you can see that there's an output file being displayed. And after outputting that file, we can see that it was successful. Next, Eric's going to be talking about the issues and challenges that we had.
So a little bit about the challenges. First, like limitations in our open source documentation and web resources played a big contributor in our project. And we had a slight effect on how fast or slow our outcomes and project came along due to this. And trial and error and digging around a lot was another contributor. Another thing that we noticed was a lot of the commands ran, obviously they had to have precise, and some may not have worked for our specific environment. So once we got the hang of what was needed, it was a lot faster and efficient, and we were able to handle more repetitive tasks easier. The only downfall to this was the accuracy was the utmost importance. Um, Another thing that we noticed was configuring the file was hard to, but not exactly. But what we noticed was we had to make a lot of adjustments to our instance that affected the outcome of certain operations running on our project. And then certain repos gave us trouble, but we were able to backtrack and solve our own problems on the way. Next, I'll be talking about future goals and high-end projects that we can do after this. So future goals and high-end goals that we could do with we could do the Flux API to run jobs. It could help deliver contactless digital receipts directly to customers' baking apps on a real cluster with real users and workloads. It'd be more desirable for us to have a dedicated management node, which would provide services for the other nodes. So another thing we could do, we could set up Flux to not allow jobs to run on it, but the nodes would still be defined as part of the Flux clusters since we'd run Flux services on it. And then another thing that we noticed that we could do after this, if we were given maybe 2 or 3 more weeks for the project, would also be prologue and epilogue. We could go on to a real cluster. It would allow for stuff to run before users' jobs or after. And then we could set up stuff for a job and things to double check that certain commands are good or certain things are good. These are the tools used for our project and our references. And if you guys have any questions, we're at the end of our project.
Yep. Thank you, Eric and Christine. So any questions for Eric and Christine about what they worked on?
Any questions here in the room?
I'm wondering if it's great that you guys have those challenges. I'm wondering, have you documented those for future? So that's good to learning, and then maybe we could improve our documentation for Flux. Maybe that was part of this.
Yeah, so Dave actually mentioned that it's a possibility that next year's intern implement Flux for their cluster build instead of Slurm. So I thought it might be good to write down like a Flux troubleshooting portion. You can see it on the wiki page actually. It's under Flux installation. So I documented all the troubles that me and Eric encountered. Yeah, I think it'd be really useful in the future if any other interns want to install Flux on their cluster, they can just refer to that page.
Awesome.
Yeah.
So I
was going to say one more thing, and I mentioned that, Flux is a completely open source project. So, if Eric and Christine, you wanted to get into this more, that's one way to start contributing is you could feed back to the project, recommendations or pull requests on how the documentation could be fixed or improved. I know you might not feel super confident in that today, but it's certainly something that is possible for anybody to do that gets into it since it's completely open source.
The Flux team would welcome that.
Yeah, I see Chris mentioned that. He's actually on the Flux team.
Yeah, I think Jane had a question.
Yeah, thanks. I was curious, were you two familiar with like resource managers or your queuing systems like Slurm or Flux before this summer?
I was actually not. Last summer I was working with Argon, but we didn't use Slurm or anything like that. This is my first time.
Okay, cool. And I'm curious, did you happen to find like Slurm or Flux more intuitive or easier to work with?
I feel like it was more easy to work with. Flux, we kind of ran into more issues than Slurm for me.
Okay, good to know. Well, thank you for presenting.
Lastly, I'd just like to thank Dave, Rico, and Martin for helping me throughout this summer. I had a great time. Thank you.
Hello everyone. So our project for the summer was to install and configure Lustre on some KVMs. And Lustre is a parallel distributed file system used on certainly our HPC systems here at the lab, but also on many HPC systems in the world. So just a brief introduction. So like I said before, my name is Naomi. I'm a senior at the University of California, Davis. I'm majoring in computer science, and I expect to graduate by the end of this year.
I'm Gabe Maxfield. I'm a sophomore at Brigham Young University, also studying computer science, and I will be graduating sometime in 2025.
So our mission was to find a scalable file system for our HPC environment. We decided to create a small proof of concept cluster on some KVMs, or kernel-based virtual machines. So our goals were as follows. So we wanted to investigate and research Lustre as a file system, see what it was capable of, and how to implement it on our HPC clusters. So we created a miniature Lustre cluster utilizing 3 CentOS 7 KVMs. And then finally, we wanted to install and investigate a backend file system for Lustre. So we had 2 options, ZFS or LDiskFS. And for reasons that we'll get into in a bit, we chose ZFS. But basically, it is just better at memory management, so we chose that one. And then after we were done installing it, we wanted to run some benchmark tests, mainly just comparing Lustre utilizing some JBODs, which stands for just a bunch of disks, to Lustre utilizing its local memory, and compare its speed with and without Ethernet.
So why we first went with Lustre, in an HPC environment that we were working under, we really desired a scalable, powerful file system and Lustre really lent itself to that with its exascale capabilities. With the way that the Lustre architecture is set up, we'd be able to increase the storage capability by adding additional servers. And so Lustre was able to provide a larger storage solution than any handful of small servers could on their own. And so that combined with the data integrity lent from the ZFS file system, which we can talk about more, really helps in an environment where you have lots of disks, lots of possibilities of hardware failure, and to be able to make sure that the data is not lost in such cases and is accessible is really desirable in an HPC fast-moving environment. We also liked the parallel nature of Lustre, where we would be able to have high throughput with reading and writing, and all of this while maintaining POSIX compliancy.
So I just wanted to get into the Lustre architecture a bit. So we have the MGS, so this stands for Management Server. It stores configuration information for all Lustre file systems in a cluster, and it provides it to the other Lustre components. And then you can see in this kind of gray blue box in the top of this diagram, we have the metadata services, which consist of the metadata server, and it manages names and directories on the Lustre FS file system. And it also handles network requests for MDTs. The MDT stands for the metadata target, and it stores the metadata. So things like the file name, file size, access time, etc. And then in the pink box to the right on the diagram, we have the object storage services. And this consists of multiple object storage servers, which manage between 2 to 8 object storage targets in a typical Lustre file system. For our project, though, we just wanted to keep it simple, and so we had 1 object storage server managing 1 object storage target. And the object storage server also provides networking requests for OSTs and services IO requests. And then we have the OST, which stands for the object storage target. it actually has the raw data. And then finally, in the gray box on the left-hand side, we have the clients which will actually access and use the data.
So while installing the Lustre file system, we had to make a decision about which backend file system we wanted to use. So the actual file system used to store the files, and so by default, Lustre comes installed with the LDisk FS file system, the Lustre disk file system, which was specifically designed for Lustre. It's a modification of the ext4 file system, and for our purposes, we decided to go with ZFS because of its larger file size, larger max volume size, the good data integrity and data protection built into the ZFS file system, including RAID support and online file system repair. And so in an HPC environment, being able to have that redundancy built in to be able to make sure that we don't lose any data, as well as the ability to scan for hardware failure while being online is definitely a benefit in such cases where if a hard drive fails, it's better to be able to repair that online instead of having to turn it offline and run file system check in order to make sure that see which bad blocks there are, like what other errors there are. And so to be able to have that seems like a really powerful tool to have in an HPC environment.
All right, so what we accomplished. In the end, our setup consisted of 3 CentOS KVMs with a single MGS, MDT, and MDS installed on one KVM. On another KVM, we had the OSS and OST, and then on the last one, we had the client. So altogether, this consisted of a small Lustre cluster built from source utilizing a ZFS backend file system. And then due to some of the challenges we faced and due to time constraints, we were not able to accomplish our benchmark tests, which would have compared the speeds of Lustre utilizing local storage versus utilizing JBODs. But this can be left to a future endeavor with Lustre.
So speaking of some of the challenges that we faced, it was really difficult to get Lustre running. For some of these, for some of this, it was because the tutorials that we were following were using an older RHEL version. We were using CentOS 7.9, while the tutorials were written for 7.3, and it seems like some of the Lustre tools have updated. And so being able to find some documentation on that was kind of difficult. It's more of like a niche technology, and so it seems like a lot of the discussion wasn't online available, and so we did find that following the Lustre manual was one of our most helpful resources. We were able to figure out what issues we were having and how to solve them because of that, and so that was a really helpful tool in our case. And then as far as installing Lustre, since we were going with the ZFS file system, it was difficult to find the RPMs and the packages necessary. Right now, from what we understand, we could only get support for the Lustre disk file system from the repository with the RPMs available, and so we ended up building from source, which had its own issues as far as configuring the packages and getting the development environment set up, and so those lent to some more challenges. And then again, just configuring Lustre with LNet, getting all of that set up, and getting the Lustre file systems mounted and created was also something that we were struggling with, but we were able to overcome. And ultimately, we did get a proof of concept Lustre cluster working on our kernel-based virtual machines.
All right, so some future possible goals we thought of. So we could make it have high availability. So the concept behind this is high availability is kind of done by replicating hardware or software. So in the event of like a server going down, for example, another one can be switched in to manage the data. so it's not lost. And we would do this utilizing the pacemaker software. Another possible goal, we could explore hierarchical storage management, or HSM. And the idea behind this is, say you have cold data, which is data that hasn't been accessed in quite a while, being stored on a high performing storage platform. Ideally, you would want to move this to a slower but also cheaper storage medium automatically, so it would be invisible to the end client. And then finally, we considered exploring a cluster trivial database, or CTDB. And what this is, it's a network-based cluster framework and cluster database platform, which allows multiple servers to run seamlessly on Lustre to serve data utilizing the server message block protocol, which is for Windows. So basically, we would be applying the SMB protocol and matching it with Lustre, which would extend file system support for different clients and operating systems, namely Windows in this case. All right, so here are our sources. If you're really interested in Lustre, I would suggest starting at the wiki. That was kind of the main hub for all of the other resources we were able to find, and it's also where I got that cool diagram from. So like I said, if you're interested, that would be a great place to start. And yeah, that's our presentation. Thanks for listening. If you have any questions, please feel free to ask.
So today we're going to be presenting on our investigation of RabbitMQ and Kafka and their benefits and drawbacks as message broker services. Our mentor for this project was David Fox. My name is Lindsey Amaro. I go to Cal Poly as a math student, and I'm expected to graduate in June of 2024.
Hey everyone, my name is Prabhleen. I go to San Jose State and I'm studying computer science. I'm expecting to graduate in May of 2023. So just to get started, we kind of just want to talk about what is a message broker and why we might need it. So normally to send messages, we would have used a TCP, but there are a lot of drawbacks with a TCP. Just a couple of them include that it has a slow start. Data congestion causes message sending to slow down, which makes it so that it can't really handle too many messages at once. And also it would need to hear a reply before it would have moved on to the next task. So as a solution to these drawbacks, we use message brokers. Here's a little basic diagram of a message broker. Pretty much sits in between two services that would interact and essentially just allows communication between two applications or machines. Here are a couple of the benefits that would counteract the drawbacks of something like a TCP. So what's great about message brokers is that they will hold messages until they're ready to be received. And they also don't require the sender to really know too much about information about the receiver. So obviously, the multiple processes facilitates decoupling, which is really great because it significantly improves system performance.
So to talk a bit more about RabbitMQ, it's a message broker service, as Prabhleen explained in the last slide, and how its sending of messages works. It starts with a producer that sends a message to an exchange. There are different types of exchanges that send messages in different ways, but the general purpose of them all is to take a message and direct it to the appropriate queues. Once that message is sent to a queue, the consumer is then able to access that queue and read the message from it. This completes the message sending process, and once the consumer has read the message, it's then deleted from the RabbitMQ server, which is a big difference between RabbitMQ and Kafka, where on Kafka, the messages stay in the Kafka server. Some general use cases for RabbitMQ include situations that require complex sending patterns or applications that need to work with certain messaging protocols like AMQP. And generally, RabbitMQ is more suited for smaller data sets, whereas Kafka is better suited for larger data sets. There are several companies that use RabbitMQ. And so for this reason, it's a fairly popular message broker service.
Okay. So Kafka is, it does have the ability to send messages. However, this is only one of its use cases. It actually has a lot of capability and a lot of other use cases. And like Lindsey explained, it's generally used in an environment that's handling a lot larger sets of data. So for this reason, it's primarily referred to as a distributed event store and streaming platform. It can be deployed on hardware, VMs, containers, and cloud environments, and it's actually very popular. So, little fun fact, it's used by over 80% of the Fortune 100 companies. Another great thing about Kafka is that it can actually be deployed in a cluster environment. So here's a little diagram of how that would have looked. So in this case, it's run as a cluster of servers that can span multiple data centers. And this is really great because it makes it highly scalable and fault tolerant. So if any of the servers fail, the other servers would be able to take over the work and just ensure continuous operations without any data loss.
Our objectives for this project were to firstly install and configure RabbitMQ in a student cluster environment. We also aimed to create basic sending and receiving Python applications for these services. And finally, we hoped to explore HPC use cases for the message brokers. In installing RabbitMQ and Kafka, on one of our compute nodes with a Red Hat Linux distribution, it involved a few main steps that you can see here on the screen. And once we completed those steps, we were able to create a simple sending and receiving applications through RabbitMQ that sent and received a hello world message. To do this, we used the Pika Python module to connect to the RabbitMQ server. And to the right here, you can see some example output from that application.
Yeah, kind of a similar process here with the Kafka install. Here's the steps we use to download and install Kafka. And we actually created a producer and consumer program on separate nodes using Kafka producer and Kafka consumer APIs, which are provided. And yeah, here's an example of the basic Hello World application across the nodes.
In our investigation of these message brokers, we found that they are also used to send tasks and jobs in addition to sending messages. And so this motivated us to come up with the use case, which you can see here on the right, where RabbitMQ and Kafka are working together in order to handle jobs issued by syslog. We're going to kind of divide up this use case into two main parts, and we'll talk about the first part now.
Okay. So the first part of this demo that Lindsey just explained actually mostly uses Kafka. So this is pretty much transferring task messages from syslog. So what's happening is the Kafka producer is continuously reading these syslog messages, but some of these messages are going to be generic messages, and some of them are going to be, task messages that we want to handle. So the generic messages are going to kind of be ignored, and these task messages are going to be published to a Kafka topic here. A topic in Kafka is pretty much a category name in which records are stored and published. So it's essentially just a log of events. So after the data that we need to transfer over is in the topic, what we have is a Kafka consumer that's reading from the Kafka topic. And to streamline this sort of process, we actually combine the Kafka consumer with the RabbitMQ producer.
So once the RabbitMQ producer receives the task, it's then in charge of delegating that task to the correct node. So for instance, say that we want to do some type of GPU job, that RabbitMQ producer would decide, okay, well, I have a RabbitMQ agent on this node that's particularly good with GPU jobs, so I'm going to send it to that node. So the RabbitMQ producer will send the job to the correct node. That node will then do whatever task is necessary, and the RabbitMQ agent will then send a task completion message back to syslog. This part is important because if we look back at the full diagram, the Kafka producer is still continually reading from syslog messages. So once it gets that task completion message, it's going to post that task completion message to the Kafka topic. And this leads into the final part of our use case, which is the Kafka reporter program. So this separate program, when we start it up, would read from the Kafka topic. And because a feature of Kafka is that it stores everything sequentially, it would be able to store a chronological list of when each task was issued and when each task was completed. So this would be useful for general reporting purposes. And this would complete our use case and in general represents an alternate way of handling jobs.
So a couple of challenges that we faced throughout this process, we found that most of the the issues we ran into was during the creation of the demo that we just explained. So like we said, we actually only wanted to handle certain messages that were being streamed from syslog, but we found that there wasn't really any straightforward method for filtering data that was sent into a Kafka topic. So that was a little bit of a challenge, and we had to find a workaround. Also, we mentioned that Kafka works in a little different environment that handles larger sets of data. But however, we have limited access to such large sets of data, so it was a little bit of a challenge to find a use case to fit Kafka into. And just adding on to that, because of the difference in the environments that you would typically see RabbitMQ and Kafka, we really wanted to highlight their benefits and drawbacks in one use case, with similar functionality. So finding a practical model to fit both services into a single use case was also a little bit of a challenge.
And coming out of this project, some future goals that we would have, we would have liked to explore clustering with RabbitMQ and Kafka. So expanding our Kafka and RabbitMQ servers from one node to a full cluster of nodes. In addition, we would have liked to explore additional clients and usage models. So writing Kafka and RabbitMQ applications in other programming languages besides Python, as well as integrating other services with RabbitMQ and Kafka in order to enhance their functionality, such as Celery with RabbitMQ or Kafka Streams with Kafka. And finally, we would have liked to explore data retention and management with Kafka. So because Kafka keeps all of its messages on its server, we would have liked to investigate when is there a certain time when we would want Kafka to delete messages from its server, or just in general, how do you handle all of those messages that it stores? So these were some of our future goals for the project that could be investigated. And here are our references for this project. And this concludes our presentation. Thank you all for listening, and if anybody has any questions, please feel free to ask.
So I have a question.
All right, thank you. Yeah, go ahead, ask questions. Yeah.
Yeah, this is Todd. The question is, I saw that the difference between the two, well, at least one of them was data retention with Kafka. And your last future bullet sort of addressed where I was thinking, but I'd like to hear how you dealt with this if you had to. And that's simply storage provisioning with Kafka when you were setting up, your test environment there. Did you have to do that? Was that an additional step with respect to, that versus RabbitMQ?
I think in regards to the data management of Kafka, I think that was more of a future goal. So we weren't able to, because of just time constraints, we weren't able to investigate kind of like how that data retention and management would have worked. But it definitely would have been a future goal because, yeah, that's one of the big differences between RabbitMQ and Kafka is that Kafka keeps all of its data on its server. So I think that would definitely be something useful to look into in the future, like kind of how those configurations work and how to in general configure the settings for Kafka and how it stores its data.
So is it fair to say that Kafka was saving some amount of data, whatever the default, capacity was, or was it acting more like RabbitMQ in your test in terms of just letting it go and not saving it?
Yeah, Kafka was definitely Kafka was retaining the data, whereas RabbitMQ was deleting the data. It would delete its data right from the server once you read it. So like there was a function in in Kafka where you could specifically like read from the beginning of the topic, and then it would show like all previous messages that had been sent to the Kafka topic. Whereas with RabbitMQ, once you stopped and started the server again, if you went back to a message queue, there was no way of seeing like previous messages that had been sent to that queue. So yeah, that was a big difference between them.
Great, thanks.